Was begun on this shot. Two sets of buildings were erected of steel frames with two different types of wall paneling. Theory predicts that as positive phase duration is increased, the peak pressure required to cause a given level of damage is decreased for certain target types. In order to obtain positive phase durations differing by as much as 10 to 1, two shots are required for the study. One with a nominal yield in the kiloton range, and the second in the megaton range. For example, the Teapot buildings were to be exposed to a positive shock phase duration of less than 1 second at 3 to 7 psi, while later in the Pacific, it is planned that duplicates of these same buildings are to be exposed to a large yield positive phase duration of 5 to 8 seconds at lower overpressures. Since the water blast line afforded the possibility of a clear or ideal shock wave with classical free air characteristics, a study was set up to determine the structural response of fighter aircraft horizontal stabilizers. 6 F-80 and 3 F-86D stabilizers were mounted vertically at a high angle of attack to obtain lethal gust loading. Rounding out the blast program were miscellaneous projects concerned with military equipment, field-type fortifications, machine gun emplacements, dugouts, and trenches. Since the drone program required daylight for operating purposes, MET had the further distinction of being the first daytime tower shot ever fired at the Nevada test site. While the expected yield was 28 kilotons, radiochemical analysis indicated a yield closer to 22 kilotons. The results of the surface blast program on the MET shot turned out to be largely as expected. A pronounced precursor formed over the asphalt line due to the high absorption of thermal radiation. The strong precursor effects extended over a greater distance than over the desert blast line. In general, the greatest drag force was measured on the desert line where dust density was greatest. Dust loading of the blast wave apparently contributed to the high total force instrument readings. Actual existence of the high total force was qualitatively confirmed by jeep damage, which was much greater than on the asphalt line. On the water line, blast perturbations were observed within 2,500 feet of zero, and jeep damage in this area was greater than on the asphalt line. Essentially, ideal shock forms were observed over the water in the next 500 feet where the aircraft components were located. F-80 stabilizer damage was greater than expected, varying from complete destruction at the inner range to moderate damage at the outer range. However, the F-86D components received overpressures as high as 12 psi with no visible damage. Good data on high-level elastic loads were obtained. A project that aroused high interest on MET concerned nuclear fireball lethality to basic missile structures and ceramic materials. Light television towers were used to mount 10-inch solid steel and aluminum spheres, hollow steel cylinders, and aluminum spheres with ceramic inserts. Specimens were also placed in the shot cab. The first tower was only 60 feet from the shot tower, with 4 others erected close behind in a descending pattern. Although it was anticipated that most specimens would be lost, all except those in the cab were recovered. Observations indicate the greatest metal loss was 1.15 inches on the radius of the closest aluminum sphere. Out along the water blast line, several stations had samples of ceramics exposed to evaluate thermal shock resistance. At a remote station on the desert line, a parabolic mirror was set up to concentrate radiant energy on ceramic specimens. Post-shot visual examination revealed severe glazing from the high thermal flux. Cloud growth studies were made throughout the Teapot series. The life history of each atomic cloud was recorded by time-lapse photography from birth to eventual dissipation by winds at altitude. Analysis was made of the influence of weather parameters on cloud evolution. While radiochemical sampling of atomic clouds is now routine procedure, special penetrations were made on Teapot to determine the radiation hazard to flight crews and to evaluate the contact radiation hazard from contaminated aircraft to ground crews. It was found that penetrations as early as 15 minutes after detonation could be made without significant radiation hazard to flight personnel. Surveys of aircraft contaminated from early cloud penetrations established a correlation between standard gamma meter readings and the actual contact radiation hazard, and indicated that maintenance and service work could be performed by ground crews without radiation injury. One of the most important single projects of Teapot was the drone blast study on METSHOT to investigate lethal effects of blast on aircraft structures in flight. 3 drone F-80 jet aircraft were to fly at 3,800, 4,300, and 5,100 feet above the shot tower. For evaluation purposes, it was necessary that the aircraft receive a single-peak ideal-type shock wave. It was planned that the drones would receive severe, moderate, and light damage, with the possibility that the lower drone would be destroyed. A prerequisite of this test was information as to where the incident and the reflected shock waves would merge over the fireball. Past tests indicated that the reflected shock wave is greatly accelerated as it passes up through the fireball and could merge with the incident wave. This point of merger and the overpressure versus distance after merger had to be accurately predicted in order to position the drones. Therefore, on development shots, Turk and Apple I, blast measurements were made from parachuted canisters and by rocket-laid smoke trails and shock photography. Analysis of these data indicated that the desired test conditions would occur at the altitudes of interest. Operations for the project were based at nearby Indian Springs Air Force Base. Rehearsals with the drones and the control craft were frequent, since split-second timing was essential to success of the mission. For easier identification, the top half of each drone was painted with a bright fluorescent color, while the bottom was painted white to reflect thermal radiation. Each drone was completely instrumented for input and structural response data, which were necessary for empirical correlation with analytical prediction of loading and response parameters. Instrumentation was designed not only to record, but also to telemeter data to stations on the ground. Under the canopy, a set of cameras was installed to record those crucial seconds when the blast hit the aircraft. The instrument panel was photographed as well as each wing and the tail section. Provision was made to eject the entire unit and lower it by parachute should the aircraft become unflyable. Each drone plane was accompanied by 2 mother aircraft, one in control and one as standby, while 2 chase planes tagged along, armed to shoot down the drone in case of malfunction. The decision for detonation of MET was dependent upon the position of the drones, and provision was made for cancellation of the shot at any time up to H-hour minus 30 seconds. As a safety precaution, the direction of flight was planned so that any damaged or destroyed aircraft would crash into the uninhabited area to the northeast of Frenchman Flat. High-speed photography records the path of the drones as they pass through the shock wave above the fireball. The wingtip instrument pods of the bottom drone are blown off and drop in an arc to the ground. The bottom drone, en route to the emergency landing strip after the burst, crashed because of loss of control before landing could be accomplished. The middle drone was landed successfully on the Dry Lake emergency strip, while the top aircraft was brought back to Indian Springs. There, the nose wheel collapsed after landing, and a pileup occurred at the end of the runway. The 3 aircraft had been positioned to receive severe, moderate, and light damage from the shock wave. In general, less damage was sustained than expected. The yield was lower, and thus the blast was lower than expected. Studies of the results will have important application in air defense problems to predict in-flight response for other aircraft types. The most unusual of the Teapot series was the HA shot, planned to be released from a drop plane at 50,000 feet for detonation at an altitude of 40,000 feet. Never before had an atomic bomb been detonated at such a high altitude, nor was it easy to erect a blast line in the sky on which to attach instrumentation. The objective was to determine the magnitude of the basic effects, blast, thermal, and nuclear radiation, in a rarefied atmosphere in order to facilitate progress of the air defense program. These data, along with diagnostic-type data, would be of great value in analytical studies and extrapolations of weapons effects to altitudes of 100 to 150,000 feet. The low-altitude device Wasp Prime, was airdropped to burst at 800 feet above terrain, or about 5,000 feet above mean sea level, and the effects and yield were measured. Predictions for the high-altitude burst indicated a slight increase in the lethal radius of thermal radiation, a small decrease in the radius of lethal blast, and a significant increase in that of nuclear radiation. For the HA shot, 8 jet aircraft were to lay smoke trails in horizontal rows 400 feet apart and 2,000 feet above the estimated point of burst. Photography, recording shockwave movement relative to the smoke grid background, would determine free air peak pressures versus distance. Then, the dropped plane would release the weapon, followed by a cluster of smoke grenades, which would be photographed to determine arrival time and particle velocity as a function of time. A string of parachuted canisters would be released next to form an aerial blast line to record effects data and to telemeter pressure information to stations on the ground. Operations base for this project was again the Indian Springs Air Force Base. The instrumentation loaded into the canisters consisted of threshold and fission detectors to measure neutron flux, pressure gauges to measure overpressure, and film badges and dosimeters which were fastened to the inner circumference of the canisters to record total dose of radiation. It was anticipated that the pressure range would extend from 10 psi to 1/2 psi, and radiation from 40,000 rem, or Röntgen equivalent man, down to 25 rem. Some thermal effects instrumentation was also carried by the drop plane. HA was scheduled as a daytime burst. Burst 0 was a point about 6 miles high above Yucca Flat and several miles north of the control point. Some blast and thermal measurements were to be recorded by instrumentation on the ground. Total thermal energy, total irradiance, and spectral distribution versus time were obtained from calorimeters, bolometers, and spectrometers. Camera stations were located at selected ground points to obtain high-resolution photography of smoke trails to determine free air peak pressures versus time and distance, and to determine effects of rarefied atmosphere on shock pressure. It was essential to have an absolutely clear sky with wind speeds at all altitudes below a certain maximum. From the ground, the drop plane was almost invisible to the naked eye. An engine failure resulted in the use of a previously established alternate release altitude of 46,000 feet, giving a burst height of 37,000 feet above sea level. An important factor contributing to the success of this shot was the Air Force capability to make successful cloud penetrations at extremely high altitudes to obtain samples for radiochemical analysis. The radiochemical yield for HA was 3.1 kilotons. Studies of the two shots indicated that there is no significant change in the partition of energy at 37,000 feet. However, a one-to-one comparison of the weapon effects for the two shots, with a significant variable being the change in ambient atmosphere, indicates that the aircraft kill radius for thermal radiation was slightly less on the high-altitude shot, while that of blast was essentially the same. For nuclear radiation, however, the immediately incapacitating and quickly lethal level of 5,000 Röntgens had a radius of 2,350 feet for the low-altitude shot against 4,700 feet for the high-altitude shot, an increase of 100%. The great increase in the lethal volume of nuclear radiation is the most significant effect of a high-altitude detonation as applied to air defense against manned aircraft. A summary of military effects studies during Operation Teapot indicates that while important investigations were made of surface and underground parameters, the greatest emphasis was placed on the potential use of atomic warheads against hostile aircraft and missiles. Vital data were obtained on the effects of nuclear detonation at high altitudes and the lethal effects of blast on aircraft in flight, problems of the utmost concern to the present and future air defense of this country. Operation Teapot now takes its place as a significant contribution to our ever-growing encyclopedia of atomic weapon research.